In this lecture, we'll talk about inferences about two means when dependent samples are involved. And these are the Chapter 11 slides. And in the slides are background notes and other examples. And we'll go right to the lecture notes. In particular, this section covers hypothesis tests for the difference between two population means when the study uses dependent samples. This is section 11.2. And we're going to start with a refresher on t-tests. Some studies in the hypotheses investigate not just one population mean, but instead investigate the difference between two population means. If a hypothesis involves the difference between two population means, and if a study uses dependent or matched pair samples, and if the population of differences is normally distributed, or the sample size of differences is more than 30, and also if this inequality is true, and importantly, if the population standard deviation of the differences sigma is unknown, it is best to test this kind of a hypothesis by using a probability distribution called Student's t-test and Student's t-distribution. This distribution came up in section 10.3 and in section 9.2, so we've seen this distribution in other sections. And just as a reminder, this is a symmetric distribution. It looks similar to a normal distribution. The mean, or the center, of the t-distribution is 0, and its test statistics can be calculated with this formula. Student's t-distribution is approximately normal if either one of these is true. Either the population on which it is based is normally distributed, or if the sample size is large, in particular if it's more than 30. Also, the larger the sample size, the more the t-distribution approaches a normal distribution. The hypotheses tests in section 11.2 will meet all of these conditions for using a t-distribution, and for this reason, the formulas and the probabilities for these hypothesis tests will be based on the t-distribution. And again, these hypothesis tests are in general called t-tests. Let's take a look at the first example. Example 1a of a hypothesis test involving the difference between two population means and using dependent samples. This is similar to exercises 10 and 11 in section 11.2 of our textbook. To test whether sleep deprivation has an effect on critical thinking skills, a psychologist obtained a random sample of 12 individuals and asked each individual to take two memory tests, one test after a full night of sleep and another test after a night of no sleep. She then recorded the test scores of each individual and then obtained the following data. Here were the results of their memory test scores. Here's the no sleep, here's the full sleep. These numbers up here represent different individuals. So this would be like individual number 1, individual number 2, individual number 3. So each individual has two test scores. Also note that it has been determined that the population from which the sample of memory test score differences is derived is approximately normally distributed. Does the evidence suggest the mean memory test score after a night of no sleep is lower than the mean memory test score after a full night of sleep? Use an alpha of 0.05 level of significance. We'll start with summarizing the information and identifying any point estimates. We're comparing mean memory test score with no sleep to mean memory test score with a full night of sleep. There are two memory test results, with no sleep and with full sleep, paired to each subject. In other words, the samples consist of matched pair data, and therefore the samples are dependent. To compare each result with its appropriate partner, we will examine the differences between these pairs. And to be consistent, we'll find all these differences by subtracting memory score after no sleep minus memory score after full sleep. So these are matched pairs. These two results, for example, 79 and 91, those were the two results of memory scores for this individual, for individual number 1. And they're paired up with each other. To make a fair comparison, all we'll want to do is just compare those two results from that individual. It wouldn't make sense to compare this result from this person with no sleep to this result of this person who had full sleep. They're two different people. So these are paired up. And we'll find all these differences. We'll do no sleep minus full sleep. So 79 minus 90, that's negative 11. 80 minus 89, that's negative 9. 67 minus 76, that's negative 9. And we'll do all that subtracting, and we'll get this new sample result of all these differences. And for the rest of the hypothesis, we'll only be using these differences as our results and in our calculations. One other thing to note is that since we're subtracting no sleep minus full sleep, when you get a negative difference, like this one, negative 11, that's indicating that the no sleep memory score was lower than the full sleep memory score. And on the other hand, if your result is positive, that's indicating that the score with no sleep was higher than the score with full sleep. So to better understand all of these differences, we'll have to calculate the mean and standard deviation of these differences. One way would be to use these formulas. These formulas, they look a little different, but they're just the formulas for a sample mean and a sample standard deviation. Now we're using D because D represents the fact that we're only using these differences. So D just stands for differences. And so this would be the mean of all those differences, and this is the standard deviation of all those differences. For now, I'm just going to show how you would do this on the calculator, and it's the same steps as you would before. So you would take these steps on the Casio calculator, take these steps on the TI calculator, and you will come up with a mean of the sample differences as being negative 5.25 test points. And the standard deviation of the sample differences came out to 6.283 test points. The mean of the sample differences, negative 5.25, is negative, indicating that mean memory score after no sleep was lower than mean memory score after full sleep in this sample. However, we'll want to test whether the mean of the sample differences is sufficiently negative, in other words, sufficiently lower than 0, and therefore sufficient to conclude that the mean memory test score after a night of no sleep is lower than the mean memory test score after a night of full sleep. We'll state the hypotheses. So these hypotheses are involving two population means, and for that reason we'll use mu1 and mu2 to represent population means. In particular, mu1 is going to be the population mean memory test score after a night of no sleep, and mu2 is going to be the population mean memory test score after a full night of sleep. So here are the hypotheses using symbols. The null hypothesis is that the mean memory test score after a night of no sleep is just about the same as the mean test score after a night of full sleep. And then the alternative hypothesis would be that the mean test score after no sleep is lower than the mean test score after a full night of sleep. And again, for clarity, I've written out these hypotheses in sentences. And on the homework or a test or your own research, you can write the hypotheses in this way, using these symbols. But for this particular hypothesis test, sometimes it's more helpful to express the hypothesis in a slightly different way, in particular in terms of the population mean difference, since our calculations are all based on differences between the samples. So another way to write the hypotheses is to write it as mu d, and that mu d represents the difference, mu1 minus mu2. So going back to our original hypothesis, if we subtract mu2 from both sides of these inequalities, so I'm doing minus mu2, minus mu2, minus mu2, minus mu2, on this side this becomes 0, and so we get, for the null hypothesis, mu1 minus mu2 is equal to 0, mu1 minus mu2 is less than 0. And remember that up here, I'm calling that difference mu d, so instead of writing it like this, I'll just call that as mu d. This is another way to write the hypotheses. This is just saying that the difference between the means is 0. In other words, there's no difference between the two means. And then the alternative would be that the difference between the two means is less than 0. In other words, there's a negative difference. Step 2 would be to verify the requirements for this hypothesis test. And the requirements are that the sample must be a random sample, the samples must be dependent or matched pair samples, the student's t-distribution must be approximately normal, and for that to be true, the population of differences on which this hypothesis is based must be normally distributed, or the sample size of the sample differences must be large, in particular more than 30. And then the last requirement is that the trials must be in effect independent, which we can check by checking this requirement here. So number 1, the sample must be a random sample. Well, in the study they do mention the psychologist obtained a random sample, so that's taken care of. Number 2, there are two results, memory test score with full sleep and memory test score with no sleep, obtained from each individual. The full sleep test score and corresponding no sleep test score of each individual therefore are matched pairs. There are two results linked to one person. In other words, the samples are dependent. Our next requirement, the normality condition. Here the sample size is small. These were only 12 individuals in this study, so it's less than 30. But fortunately, the description of this study does mention that the differences in the memory scores are approximately normally distributed. So that means that we still satisfy the normality condition. And then the fourth requirement, the trials must in effect be independent. So we have to check this condition. N is 12, we can plug that in, solve for capital N. And that means that this inequality is true as long as the population size of all differences in memory test scores, capital N, is greater than 240. Since the number of memory test scores is infinite, it seems reasonable to conclude that that population is more than 240, and therefore this inequality is true, and we can conclude that the trial is in effect independent. Alright, in the next video we'll continue on to step 3 and finish this example.